problem 49. Here we have this cylinder and we have a small particle which is in contact with the inner wall of the cylinder. And the cylinder is rotating with angular velocity of omega and rotating this particle with itself. Of course, if the omega become small and small, finally this particle is gonna drop down. And if omega is too much, so because of the interaction force between the particle and cylinder and having some friction force, this is not gonna slide down. The question here, what is that minimum omega to keep this guy in its place so it doesn't slide down? Again, stop this video, think about this problem for 5 minutes, then see the rest of the video. So to solve this problem, first we need to choose a coordinate and also draw the free body diagram. If you track this particle, it is rotating on a circular plane, right, on a circle. If you look at from the top, A is moving on a circle. This particle is moving on a circle with the angular velocity of r times omega. And if you want to draw the free body diagram of it, let's do it right on this figure. We have gravitational force and normal force. And let's say this particle is about to slide down, and there is a friction force which prevents it from sliding down. The friction force, of course, is going to be upward. And because it is about to slide down, friction must be equal to mu s times n, the normal force. So the motion is circular, and we have some information about the velocity of it. So the best option here for the coordinate is normal tangential. You can use polar as well, but normal tangential is more common. This is going to be ET, and this is going to be EN. Again, if you want to draw them here, this is the normal direction. And tangential direction is to the plane, so we don't see it here. And also, I'm going to write the equilibrium equation in this direction, in the vertical direction. Let's call that direction Z, or anything you want. So based on Newton equation, sum of the forces in the vertical direction in the Z direction must be equal to 0 because there is no movement in the Z direction. From here, we can find friction force is equal to mg. So mu s times n, which is the friction force, is equal to m times g. So normal force must be equal to mg divided by mu s. And now in the normal direction, sum of the forces in the normal direction is equal to mass times acceleration in the normal direction. And if you remember from previous video, acceleration in the normal direction is velocity squared divided by r, or r times omega squared. So this is going to be equal to mr omega squared. In the normal direction, the only force we have is the normal force. And normal force is equal to mg divided by mu s. So it must be equal to m times r times omega squared. Now we found an expression for this omega, right? M is going to cancel out, which means this problem is independent from the mass. And omega is going to be equal to square root of g divided by mu s times r. So this is the minimum angular velocity that we need to keep that particle in its place.